Today we're talking about fertilization with phosphorus and potassium. This class is based on chapter 26 of the book Principles of Agronomy for Sustainable Agriculture. The chapter is authored by Delgado, Quemada and Villalobos, and it's called Fertilization with Phosphorus, Potassium and Other Nutrients. This presentation has been developed by Antonio Delgado and Francisco Villalobos. First of all, what are the roles of phosphorus in plants? Phosphorus is an essential element for plants, but also for animals. For instance, humans require more than 0.2 grams of phosphorus per day. After nitrogen, phosphorus is the main limiting nutrient for plant growth and agricultural productivity. It is involved in many biological processes, including structural functions as part of the nucleic acids, phospholipids in the membranes, but is also involved in key metabolic reactions, mostly associated with energy transfer, like the phosphorylation reactions. Phosphorus is only absorbed as the hydrogen phosphate, which is fastest absorption mode, or as monohydrogen phosphate. In case of phosphorus deficiency, the plants grow less. The high mobility of phosphorus within the plant has as a consequence that deficiency is first detected in older leaves. The symptoms, apart from reduced growth, are premature senescence of older leaves and also the appearance of purple color in leaves due to accumulation of anthocyanins. The phosphorus concentration in leaves of crop plants vary largely among species, being between 0.05 and 0.3% over dry matter. And what are the roles of potassium in plants? Potassium is absorbed actively as an ion. The absorption is controlled by the internal concentration. So, the lower the internal concentration, the higher the absorption will be. Potassium within the plant is transported mainly to the young growing tissues, and it acts as an osmoregulator, for instance in stomatal control. It indirectly promotes photosynthesis and transport of assimilates, and has a direct effect on some important enzymes. It is also involved in the plant tolerance to cold or water stress conditions. The symptoms of deficiency for potassium usually occur late after deficiency has been happening for quite a while, and many times are not clear, might be confused with deficiency of other nutrients or micronutrients. The high mobility of potassium within the plant dictates that the deficiency is first detected in the older leaves of the plant. The consumption of phosphorus is mostly dedicated to agriculture as phosphorus fertilizer. Phosphorus fertilizers in the end all come from phosphate rock, and phosphate rock is a limited non-renewable resource. The amount of phosphorus fertilizer is quite variable in the different areas and also has been changing quite a lot with time. In case of excess phosphorus, we have a severe environmental problem, which is eutrophication. That means the accumulation of nutrients in surface waters, which promotes the growth of algae and aquatic plants. Most of that phosphorus arriving to surface water is transferred from agricultural land by the sediments originated by soil erosion. In this slide we see where are the surpluses or deficits of phosphorus as a nutrient in agriculture. The red, from yellow to red colors, we show a surplus, which means that the phosphorus fertilizer exceeds the extraction made with agriculture, while the blue colors show areas where we have a phosphorus deficit, which means that we are using less phosphorus as fertilizer than that exported with the crops. In principle, we see that excess phosphorus occurs in developed countries. We see most of the United States, the West Coast, East Coast, most of Europe, China in particular, and also some surplus in India, Turkey, parts of Eastern Europe, and most of the United States. We have also surplus of phosphorus in Brazil. However, phosphorus deficits mostly concentrate in less developed countries. A lot of phosphorus deficit occurs in Central, South Africa, also in Argentina, some small parts of the United States and Eastern Europe. Also some areas of Australia. But the use in phosphorus has been changing quite a lot. Since 1960, we have most of phosphorus fertilizer was used in developed countries and almost none was used in developing countries. The amount of phosphorus has been increasing steadily since the 1960s up to now in developing countries. But something different has occurred in developed countries, where we had first an increase until 1980, then the amount of phosphorus used was level until 1990, and then it has decreased back to levels of around 1960. So the trend is that not much more fertilizer is being used in developed countries, so some deficiency might be occurring in the future, while we expect to increase the use of phosphorus in developing countries. The problem with excess phosphorus, as related to eutrophication, is the increase of algae growth in surface waters, also aquatic plants, like in this this lake, where the predominant species is yellow pond lily. The question is if the phosphorus fertilizer prices in the future and its availability will be limited. Should we be terrified about the scarcity of phosphorus, as it is a non-renewable resource? 2008 was the year of the so-called phosphorus crisis. What happened then? Well, the price of phosphorus increased from around $21 per ton up to $113 per ton in 2008. This was due to two facts. First, China reduced the export of phosphorus fertilizers, and also the production of phosphorus rock in the USA decreased. But will it be a worse problem in the future? This figure here shows a red line with a prediction of phosphorus production globally. This model predicts that the phosphorus production will peak sometime after 2030, and after that phosphorus production will be decreasing steadily, which means that the known reserves of phosphorus will be depleted in the future. That will cause an increase in prices. Here we have different model predictions of prices of phosphorus fertilizer in Africa or in the USA. All models predict a large increase in the prices of phosphorus in the future. The problem is not only that the resources are limited. The problem is also that the supply is restricted to basically three countries. China, Morocco, and USA produce around 70% of total phosphate rock production in the world. On the other hand, China, India, and Brazil consume around 2/3 of total phosphorus in the world. That means that the phosphorus is not only scarce, but is also a strategic resource. Usually, we don't have much phosphorus in the soil that can be used by plants. Soil total phosphorus is usually low, typically below 1 gram per kilogram of soil. We found phosphorus in the soil either as inorganic or organic phosphate, and only inorganic phosphate can be absorbed by plants. The phosphorus in the soil is distributed in three pools. First, in the soil solution, although it usually shows very low concentration. It can also be adsorbed to hydroxylated surfaces like oxides of iron or aluminum, or adsorbed to borders of clay minerals and carbonates. We can find also phosphorus as precipitated metal phosphates, quite insoluble, of iron, aluminum, or calcium. Available phosphorus for the plant is considered usually as the sum of phosphorus in the soil solution plus labile phosphorus. And labile means easily released to the soil solution. Usually the available phosphorus is less than 10 of total soil phosphorus. This is a diagram of the phosphorus cycle in the soil. We have the different pools of inorganic phosphorus in the soil solution, as metal phosphates or adsorbed phosphate. We can increase the inorganic phosphorus by adding fertilizer, or we can remove inorganic phosphorus by plant uptake. Plants, by decomposition, will produce organic phosphorus, and organic phosphorus may be converted to inorganic by mineralization, or may be increased by immobilization by the microbiota in the soil. The relation between the amount of phosphorus adsorbed and the amount of phosphorus in the soil solution is the buffering capacity. In this figure, we show a soil A with a high buffering capacity and a soil B with a rather low buffering capacity. As we can see, in the soil with a low buffering capacity, soil B, we have, for a given amount of phosphorus absorbed by the plant, we have a huge amount of reduction in the P concentration of the soil solution. The opposite occurs for the high buffering capacity soil, where the same decrease in total absorbed phosphorus is associated with a small decrease in the phosphorus concentration. As we said earlier, the plants absorb forms of phosphate. The active absorption occurs only as the hydrogen phosphate, which is the fastest, shows the fastest absorption, and hydrogen phosphate. The predominant form depends on the pH, like shown in this graph. For acid pH, the predominant form is the dihydrogen phosphate, while with basic pH, the predominant form is the monohydrogen phosphate. Therefore, the absorption of phosphate will be faster when we have an acid pH in the soil. The point is that roots can excrete organic acids that favor a low pH around the root in the rhizosphere, and that promotes the absorption of phosphates. Both roots and microorganisms produce acids and phosphates that contribute the acids to improve the pH around the roots, and the phosphates contributes to the generation of inorganic phosphate that can be absorbed by the roots. Potassium in the soils is much more abundant than phosphorus, as it is a component of feldspar mica minerals, which are common primary minerals. It is an abundant element in the soils with concentrations between 0.3 and 3% over total soil mass. We find potassium either in the soil solution or in exchangeable forms or non-exchangeable forms. The exchangeable form is adsorbed to negatively charged sites located on clays and soil organic matter. The non-exchangeable, also called fixed potassium, is catched in the interlayers and edges of 2,1 clay minerals. As happens with phosphorus, potassium is a non-mobile element in the soil. Here we see clay particle with its negative charge that promotes the absorption of the potassium ions to its surface. The available potassium in the soil will be the sum as the potassium in the soil solution plus the exchangeable potassium. The concentration in the soil solution typically lies between 0.2 and 10 milliequivalent per liter. It means that less than 1% of exchangeable potassium is going to be in the soil solution. It is absorbed as the potassium ion with a positive charge. The buffer capacity for potassium depends on the clay content on the soil and the mineralogy, because clay soils with 2.21 clay minerals will catch more fixed potassium than other types of clay soils. In this diagram, we see the cycle of potassium in the soil. It could also serve for magnesium or calcium. Here we have in the center the cations in the soil solution, it's considered potassium, that can be increased by by adding fertilizers or amendments containing those nutrients, can be reduced by plant uptake of these nutrients. Plants will generate residues, and from the residues, after decomposition, we will have potassium back in the soil solution. Then, potassium in the soil solution is in equilibrium with adsorbed exchangeable potassium, as we said, associated to negative surfaces, and can also be increased by weathering of the primary and secondary minerals. It can also be reduced by fixation into 2,1 crystal layers in clay minerals, and although it's very slow, can be some release of this fixed potassium. This picture shows some of the symptoms of cucumber deficiency in plants. Let's review now what are the phosphorus and potassium fertilization strategies. The problem with phosphorus and potassium is that as they are involved in different reactions in the soil, a large fraction of applied nutrients may become not available to plants. But in any case, a reserve in the soil can be built up, although only a fraction of the reserve will be available to the plants, and it is not easy to know which fraction is gonna be. The idea is that we can deduce when the reserve of phosphorus or potassium in the soil is enough to supply enough to the crops. That is based in the soil analysis of phosphorus and potassium. The idea is that if we plot the yield of the crop as a function of the critical of the soil test level, which means the amount of phosphorus or potassium in the soil, we should have a curve like that. Above a given value of the soil test level, we won't have any response. This value is the so-called critical or threshold STL, soil test level. In other words, above the critical soil test level, we should not expect any increase in yield. So for this method to work, the calculation of the threshold values for phosphorus or potassium is the key issue. Once we know the threshold values, we can apply two different strategies. One strategy is the so-called build-up and maintenance, and the other strategy is the so-called sufficiency strategy. In the build-up and maintenance, we try to keep the soil within the so-called maintenance range, which is a range of soil test level values where the crop is going to have enough. We will avoid excessive, or we will avoid deficit soil test levels. In the sufficiency strategy, on the other hand, we only apply fertilizer if we are going below the critical level. In this picture, we see a diagram showing the build-up and maintenance strategy recommended in the three-state region of the United States. In this figure, we plot the fertilizer rate as a function of the soil test level, and we plot here a critical level, which is the threshold, STL, and so-called maintenance limit, which is twice the critical level. What we do is that if we find that the soil test level is below the critical level, we will need to apply the crop export and more. That's why we plot this increasing fertilizer rate. If we are within the maintenance range, which means that we are between the critical level and the maintenance limit, we only apply the exported nutrients by the crop. If the soil test level is above the maintenance limit, we will apply less than the nutrient exported by the crop. We have different alternatives. For instance, applying 0 or applying 50% of crop exports, or apply a decreasing amount as the soil test level increases. The soil test level that we should apply for phosphorus can be different depending on the conditions we are working with. For instance, the Olsen's test of phosphorus availability is used in basic soils up to slightly acidic soils, and is the official phosphorus test in most countries of the Mediterranean countries of Europe, in the UK, and several states of the United States. Here we show the threshold levels expressed as milligrams of phosphorus per kilogram of soil depending on the conditions. We can have values as low as 4 ppm in rain-fed crops, in humid areas and medium texture soils, up to values of 25, which would be a general recommendation, which is a safe value for phosphorus concentration. For potassium, the most common test is the ammonium acetate extraction, and this table shows the threshold levels as a function of the cation exchange capacity of the soil, from 150 to 240, or depending on the texture, having a value of 100 milligrams of potassium per kilogram of soil in sandy soils, up to between 200 and 300 milligrams of potassium per kilograms of soil for clay soils. Once we make our analysis, the amount of fertilizer to be used is calculated using this equation, where the phosphorus rate is equal to exported phosphorus plus a function of the difference between the threshold STL and the actual value that we have measured in the soil. Note that this equation is only valid when our soil test level is below the threshold STL. A similar equation is used for calculating the amount of potassium, exported potassium plus a function proportional to the deficit in potassium that we have in the soil. Here we have also a factor that depends on soil texture, going from 1 to 1 to 5. If we follow the maintenance and build-up strategy, we have to take into account several factors. First, that the threshold value may not be reached very fast. It may take several years before we exceed the threshold soil test level. To check if we have already exceeded the soil test level, we'll need to perform periodical analysis of the soil to check the evolution. In any case, when using the equations, we have to avoid massive applications of phosphorus or potassium. In general, we consider that we should never exceed 100 kilograms of phosphorus per hectare per year, or 275 kilograms of potassium per hectare per year. Remember that above the maintenance limit, we should apply rates of fertilizers lower than the crop exportation, or we should not apply fertilizer at all. When should we apply phosphorus fertilizer? Well, phosphorus has been traditionally applied as a pre-plant fertilizer. The less soluble form should be applied much earlier. For instance, if we want to apply rock phosphate, we should incorporate the rock phosphate more than 3 months before planting our crop. Fractionation of phosphorus is uncommon. It is only justified in very sandy soils saturated with phosphorus to avoid leaching. It could be used to avoid massive contributions that favor retrogradation of phosphorus, and that may occur in soils very low in phosphorus, soils high in calcium, of crops with very high phosphorus demand. In any case, the fractionation of phosphorus is limited by the low mobility of phosphorus in the soil, so it is better performed if we can apply fertigation. The application localized in bands to locate phosphorus close to the roots may be performed in soils poor in phosphorus. This band application reduces retrogradation as it saturates the fixation capacity of a lower volume of soil, so applying a banded localized application is better than mixing the phosphorus with all the soil. It puts the fertilizer closer to the roots so we can increase uptake, and usually promotes early growth of crops. It has a so-called starting effect. The amount to be applied in bands is only limited if we apply ammonium phosphate because of the toxicity of ammonium. If we apply in bands, usually we should never exceed 40 kilograms of nitrogen as ammonium with the fertilizer. We should always apply the fertilizer separate from the seeds, and this is due to the possible effects of increased salinity on the emergence of the crop. In general, phosphorus applied with organic amendments, that could be, for instance, residues, or with organic matter, improves phosphorus efficiency. This is due to the fact that organic matter competes with phosphorus for adsorption sites in the soil. It also decreases the precipitation as metal phosphates. In the case of potassium fertilizers, we can follow more or less the same rules. It is applied before sowing or at sowing. Fractionation and located application in bands will contribute to saturating the soil with potassium and keep a high concentration of potassium in the soil solution. The main difference between potassium and phosphorus is that no improvement in recovery efficiency of potassium is due to adding organic matter, which is a very important factor for improving phosphorus fertility. So, For potassium, adding organic matter will only have an effect on very sandy soils, as it increases the sorption capacity of the soil. This is machinery that allows sowing and application of fertilizer with bending. Fertigation is also an interesting alternative for applying phosphorus, as it allows higher phosphorus concentration in the bulb and decreases the precipitation in that area. Phosphorus is also, or can also, interact with other nutrients. For instance, high concentrations of phosphorus in the soil usually reduce the availability of zinc for the crop. This is results for wheat, and also high rates of phosphorus in the soil increase the incidence of iron deficiency chlorosis. So phosphorus fertilization can affect the uptake of micronutrients, and if phosphorus fertilizers are enriched with micronutrients, that can have a negative effect on phosphorus nutrition. Fertilization with other nutrients should follow a sufficiency strategy, which means that those nutrients are only applied if deficiency is expected. That applies to calcium and magnesium. They both have a similar cycle to that of potassium and can be analyzed with the same extraction method as that of potassium. With ammonium acetate extraction, the threshold levels for calcium in the soil are between 250 and 500 mg per kilogram, and for magnesium between 30 and 60 mg per kilogram. In general, the threshold levels will be proportional to the cation exchange capacity of the soil. We should only expect a low availability of calcium in acidic sandy soils with low base saturation. One problem with calcium, magnesium, and potassium is that they can be involved in antagonistic effects. The optimal ratio of calcium and magnesium should be around 5. If we have a ratio of calcium-magnesium below 2, we will have calcium deficiency, and if the ratio calcium-magnesium is above 10, we will have magnesium deficiency. In the case of the ratio of potassium and magnesium, the ratio should be between 0.2 and 0.3. If the ratio potassium-magnesium is below 0.1, we will have a potassium deficiency, and if the ratio is above 0.5, we will have a magnesium deficiency. We will see now a couple of examples of the calculation of P and K fertilizer. The first example is a sugar beet cotton rotation. The expected yields are 4 tons per hectare for cotton fiber plus seed and 60 tons per hectare of sugar beets. The cotton residues are chopped and incorporated by deep tillage. The sugar beet residues are removed from the field. The soil analysis from 0 to 30 centimeters tell us that the texture is clay, bulk density is 1.3 tons per square meter, per cubic meter, Also, phosphorus concentration is 10 mg per kilogram, and acetate extractable potassium is 897 mg of potassium per kilogram of soil. Using table 13.1 in the book, we can see the table with the harvest index, and we find that cotton has an interval from 0.25 to 0.40. Sugar beet has a harvest index between 0.5 and 0.7. We take the mid values for cotton 0.32, for sugar beet 0.6. We can also find in the appendix of chapter 32 the percent dry matter for different crops, including cotton fiber plus seed, has 91% of dry matter, and sugar beet roots have 20% of dry matter. Therefore, we can now calculate the expected yields in terms of dry matter. For cotton, multiplying 4 tons multiplied by 0.91, which is the fraction of dry matter, we come up with 3640 kilograms per hectare of dry matter yield of cotton. Sugar beet, multiplying 60 tons multiplied by 0.2, we come up with 12 tons of dry matter sugar beet roots per hectare. Now we can calculate the production of residues. For cotton, we multiply the yield in dry matter, 3640, by 1 minus harvest index over harvest index. In other words, 3640 multiplied by 1 minus 0.32 divided by 0.32, and it is 7735 kilogram per hectare. For sugar beet, applying the same equation, we come up with 8,000 kilograms per hectare of residues of sugar beet. Note that only the sugar beet residues are going to be exported. Then we look for the thresholds. The thresholds may be found in table 26.2 for phosphorus and table 26.3 for potassium. We see that the phosphorus threshold is between 8 and 10 milligrams per kilogram for clay soil, or 15 and 20 interval milligram per kilogram for sugar beet. For potassium, the threshold lies between 200 and 300 for a clay soil. You can take the mean value. For phosphorus, let's see what is the strategy for fertilizer rate. We take the upper threshold for sugar beet, which is 20 milligram per kilogram. Well, this is due to having one reason for that is that we have a high yield. So, if we take 20 milligram per kilogram, if you remember, we have a threshold below, so we need to add more phosphorus than that is exported. Okay, let's calculate now the exported phosphorus. First, for cotton, no residues exported, only the harvest X exported with a percent of phosphorus of 0.41. So multiplying 0.41 by dry matter yield, we come up with the total amount of phosphorus exported, 14.9 kilogram of phosphorus per hectare. For sugar beet, we are also exporting residues, and the percent phosphorus in harvest is 0.25 and in residues is 0.22. Now we calculate the product of the yield, dry matter, multiplied by the percent phosphorus in yield, plus the amount of residues in dry matter multiplied by the percent of phosphorus in the residues. And the total is 47.6 kilograms of phosphorus per hectare. Now we calculate the average for the rotation, which is the average between 14.9 and 47.6, and we come up with 31.3 kilograms of P per hectare per year. And now we can calculate the phosphorus, the fertilizer rate for phosphorus. We use, in principle, a 2-year build-up period. We could use a different, but for the sake of this example, let's consider that we take 2 years of build-up period. It means that in 2 years we should arrive at the threshold soil test level. So we apply the equation that tells us that fertilizer rate for phosphorus is equal to exported phosphorus multiplied by 10 by soil bulk density multiplied by soil depth divided by the number of years, we have said that it is 2, multiplied by the difference between the threshold soil test level for phosphorus, which we decided that was 20, minus the soil test level that we have measured, which is 10 ppm. And applying this equation, we come up with 50.7 kilograms of phosphorus per hectare. This is the amount of fertilizer to apply every year. This may be supplied using 253 8.8 kilograms of triple superphosphate per hectare, simply by dividing 50.7, dividing that by the concentration of phosphorus in superphosphate. This amount should be added before planting cotton or before planting sugar beets. The strategy for K is also based on the build-up and maintenance equation. First, we compare the STL, the soil test level, which is 897. This is the value that we have measured in the soil. We compare that with the maintenance limit. The maintenance limit is 500 milligrams per kilogram. This is exceeding the maintenance limit, so we should add less potassium than that exported. We have already said that the alternatives in this case are or applying a fixed percentage of exported nutrient, or reduce the fraction K rate over K exported from 1 when we are at the maintenance limit, in this case 500 milligrams per kilo, to 0 when the STL is equal to 3 times the STL threshold. In this case, clearly, the STL exceeds 3 times the, the threshold, which is 750. Therefore, we will not apply fertilizer for K in this rotation. The second example is a soybean barley rotation under irrigation. The expected yields are 3.5 tons per hectare for soybean and 6 tons per hectare of barley. The growing cycles go from April to September for soybean and November to June for barley. In this case, the crop residues are left on the soil. The soil analysis tells us that we have a textured sandy loam, bulk density 1.4, OSM-P is 8 mg per kilogram, acetate extractable potassium is 200 milligrams of potassium per kilogram of soil. The organic matter concentration is 1%. In table 13.1, we look for the harvest index for soybean between 0.35 and 0.50, for barley between 0.4 0.5. We take mid values for the two crops, and then we go to the appendix in chapter 32 to look for the percent dry matter in soybean seeds, which is 87.5, and for barley grain, which is 88.5. Therefore, we can now calculate the expected yields, multiplying the expected yield by the fraction of dry matter. And we come up with 3,062 for soybean and 5,310 for barley. The production of residues is once again calculated as a function of the harvest index. So we come up with 41, 43 residues for soybean and 64.90 for barley. The thresholds, which are taken from table 26.2 for P and 26.3 for K, are between 10 and 12 for loam soils. For phosphorus, we take the maximum value, 12 milligrams per kilogram, and the K threshold between 150 and 175. For loamy soil, we take the maximum value. This is a conservative approach, taking the maximum value. The strategy for P should be, as the threshold, which is 12 milligrams per kilogram due to high yield, is above the value that we have measured, which is 8, we need to add more P than that exported. First, we calculate the exported P by soybean, no residues exported, and the percent P in harvest is 0.66. We look for that in the table of chapter 26. Multiplying dry matter yield by the concentration of P, we come up with an exported amount of 20.2 kilograms of phosphorus per hectare. Similarly, for barley, no residues exported, percent P in harvest is 0.42, we are exporting 22.3 kilograms of phosphorus. The mean for the rotation, the mean of these two values, is 21.3 kilograms of phosphorus per hectare. Now we applied the equation for situations where we need to increase the P concentration. So we calculate the P rate as exported P multiplied by and adding 10 times density, depth, number of years, and the difference between soil test level threshold and soil test level. These are 12 and 8, and we come up with 29.7. This total amount might be supplied using superphosphate, which has a concentration fraction of P in superphosphate is 0.2. So we could use 148.3 kilograms of triple superphosphate per hectare. Adding that before both soybean and barley. The strategy for K, in this case, the STL is 200 milligrams per kilogram, which is greater than the threshold, which is 175. And this value is also lower than the maintenance limit, which is 350. Therefore, we need only to add exported K. The K exported by soybean, multiplying yield by the concentration of K, is 45.6, and for barley is 28.7. The mean value for the rotation is 37.3. This can be supplied using 89.9 kilograms of potassium sulfate, as potassium sulfate has a concentration of 0.415 kilograms of potassium per kilogram of potassium sulfate. This is the amount to apply before both crops.